So at this point, we have done 5 examples of Gauss-Jordan elimination with systems that either have 3 equations and 3 variables, or they have a different number of equations than variables. And you have seen that this is a very long and tedious process. Just to do one single problem can take a while. It can take up a whole page. So on your exam, I will probably give you at most one of these, okay, one of the larger systems to solve by using Gauss-Jordan elimination, okay. So example 5 is a good way. I can also ask you a question about this whole process. Basically, I could give you the final matrix or a partially done matrix, meaning some of the Gauss-Jordan elimination has been done, but not all of it. And you need to, finish it off or just simply state the solution of the corresponding system of linear equations based off the matrix. Okay, so that would save you some time if it were indeed the final matrix or it was already partially done for you. Okay, so let's take a look at example 5. We have 3 matrices. For each augmented matrix, state the solution of the corresponding system of linear equations. Okay, so basically you will be given a matrix, okay? That matrix definitely represents some system of equations. We don't have the system in front of us, but we want to know, the system that it does represent, what is the solution to the system of equations. All right, so in part A, there is our matrix, okay? When you look at this, the first thing you should see is this row of zeros, okay? I look at this, I see a row of zeros, okay? And immediately, I know a row of zeros corresponds to infinitely many solutions, okay? So since there are infinitely many solutions, you need to parameterize the solutions, okay? So let's go ahead and do that, okay? Again, we're just going to assume that our variables are x, y, and z. You could use x1, x2, x3 like your book or my math lab does, okay? I like x, y, and z. So again, we'll assume that this first column, those are numbers in front of x. The second column, those are numbers in front of y. The third column are numbers in front of z. So if we translate the first equation, the first row in the matrix, that's going to be 1 times x plus 3 times y plus 0 times z is equal to 5. Okay, if we simplify that, we are going to get that x plus 3y is equal to 5. Okay, and then let's go ahead and translate the second row of the matrix. Okay, that's going to be 0 times x plus 0 times y plus 1 times z is equal to -4. Okay, if you clean that up, you are going to get that z equals -4. Okay, all right, so again, we have to parameterize we have to parameterize the solutions, okay? So that's when you're going to have to write your order triple, okay, using a t-value, okay? You would be in charge of the t-value, okay? So remember, this third row of all zeros doesn't help with the parameterization. It is just there to tell us that there are infinitely many solutions, okay? But it plays no role in doing the parameterization. Okay, so we got to rely on these guys, okay? One thing that you should notice from this is this statement, z equals -4. Z is always going to be -4. Always, 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 okay? So for your solution, your solution of the system of equations, the z value always, always, always has to be -4, okay? So now we need to go back to this, okay? So what you should notice, the t-value is not going to be z because we know that z has to be -4. So that means that the t-value will either be the x or the y, okay? It is your choice, okay? It could be either one, okay? So what you should do, think back to the smaller systems when we had 2 equations and 2 variables and we only had 2 variables involved. kind of z is left out because it has a specific value. You just need to solve for one of the variables, okay? I think it's easier to solve for x here, but you could certainly solve for y. So I'm going to move the 3y over. Okay, I'm going to get x is equal to negative 3y plus 5. Okay, so now when I look at this, I ask myself, okay, out of x and y, which one am I in charge of? Okay, well, I have free reign over y. If I pick the y value, then I have to multiply it by negative 3 and then add 5 to get the x value. Okay, so what's going to happen here is that the y value is going to be our t. Okay, and so then that's going to force the x value to be negative 3 times y, which is t, plus 5. Okay, so to write down your parameterization, okay, you have to give me the ordered triple, the x, y, and the z. Don't forget about the z. Okay, so the x value is going to be negative 3t plus 5. The y coordinate will be the t, the one that we get to pick, okay? And then the z value always has to be 4, okay? So this is the parameterization here, okay? So if you wanted one specific solution, okay, you just pick a t value, okay? So if we picked t equals 0, here, I'll write it right here. If we pick t equals 0, okay, and I plugged in that t value in here, okay, the x coordinate would be negative 3 times 0 plus 5. That's 5. Okay. The t coordinate would be z, so that means y would have to be 0. Okay. And the z value has to be negative 4 no matter what. Okay. So this is one specific solution. Whoops. And so that's kind of how you do this one. Okay. So let me write this here. One specific solution. All right, again, the whole point of this problem, okay, was to be kind of a time saver where you didn't have to do the Gauss-Jordan elimination all the way out. This was like a final matrix, and you saw that row of zeros, and you interpreted it as infinitely many solutions, okay? All right, let's take a look at the matrix in part B, okay? So if you saw this matrix, how would you interpret the solution of the corresponding system of equations? Okay. Again, we do not have identity on the left side of the vertical bar. Okay, but if you look at that bottom row, I see 0, 0, 12. Okay, so if you translated this last row into an equation, okay, again, assuming that the first column are numbers in front of x, the second column are numbers in front of y, okay? This would translate into 0 times x plus 0 times y is equal to 12, okay? If you clean up that equation, anything times 0 is 0, so you're going to get 0 on the left, 0 is equal to 12. That doesn't make any sense. That's a false statement, okay? So this would be the case of no solution for the corresponding system of equations. Okay. All right. So that was pretty straightforward. Okay. Last one. Let's look at part C. Okay. Here's a matrix, and well, when you look at it, it may look like not a lot has been done to it. You know, if I'm going for the identity on the left side of the vertical bar to do your Gauss-Jordan elimination, you know, I'd have to put a 1 right here, and, you know, the rest of the column zeroed out, and then you look at column 2, and there's already a 1 on the principal diagonal, and there's a 0 below it, but then you have to zero out this guy, and then in the third column, absolutely nothing has been done to it. So, you know, this would actually take some work. It is definitely not a final matrix, okay? This one is actually special. You don't have to do Gauss-Jordan elimination on it to get the solution to this system, okay? This, if you notice right here, there's a bunch of zeros right here, okay? This is called an upper triangular matrix. You don't need to know that, I'm just telling you. This is an upper triangular matrix, meaning okay, if you looked at this part of the matrix right here, that's where all the non-zero numbers are. The bottom part of it is all zeros, okay? So actually what you can do is translate this matrix into equation form, but start at the bottom and work your way up. So watch, you don't actually have to go through the whole Gauss-Jordan elimination process. It's actually easier to just write out the equations, okay? So most of our zeros are in the bottom row. So we're going to start with row 3 here. Okay, watch. This is going to be super fast and much easier than Gauss-Jordan elimination. Okay, so again, we're assuming that the first column are numbers in front of x, the second column are numbers in front of y, third column, numbers in front of z. Okay, translate the third row. It's going to be 0 times x plus 0 times y plus -6 times z is equal to 12. Okay, so clean it up. Okay, this is going to be 0 plus -6z is equal to 12. Okay, and that's an equation that we can solve for z. Okay, -6 times z. Divide both sides by -6 if you want z by itself. Boom, z has to be -2. Okay, so that was pretty fast, and we got that. We didn't do any kind of row operation. Okay, we just translated the bottom row into an equation, and we were able to solve for z. Okay, all right, like I said, we're working from the bottom of the matrix to the top. Okay, so now we're going to take a look at row 2. Okay, so again, translate row 2 into a system, or sorry, into an equation. Okay, so it's going to be 0 times x plus 1 times y plus 3 times z is equal to 8. Okay, so let's clean that up. Okay, 0 times x is 0, and then we'll get 1 times y is y, plus 3z is equal to 8. Okay, well, guess what? We already know what z is. Z is -2, so we're going to plug that in. Okay, so we're going to get y plus 3 times, we know z is -2, so let's pop that value in. Okay, that has to equal 8. Okay, all right, so now we are just left with y and we can solve for it. Okay, we're going to get y minus 6 is equal to 8. Add 6 to both sides. We get that y is 14. Boom. Okay, so now we're going to work our way back to row 1. Okay, this is going to let us get x. Okay, all right, so let's go and translate row 1. Okay, according to row 1, 2 times x plus 1 times y plus 2 times z is equal to 0. Okay, so 2 times x plus 1 times y plus 2 times z is equal to 0. Okay, let's go ahead and clean that up. Okay, 2 times x plus y plus 2z is equal to 0. Okay, we know from our other work that z has to be -2, y has to be 14. So let's pop those values in, and then we're going to be able to get x. Okay, so 2 times x plus y is 14, so I'm going to pop that in. Okay, plus 2 times z is -2, so substitute that value. Okay, that is equal to 0. Okay, all right, so let's simplify this. This is going to be 2x plus 14 minus 4 is equal to 0. Okay, so we're going to get 2x. Let's combine our numbers. 14 minus 4 is positive 10. So 2x plus 10 is equal to 0. Okay, we want to get the 2x by itself so that we can solve for x. Okay, so we'll move the 10 over. So 2x is equal to -10. Okay, divide both sides by 2. Okay, that's going to tell us that x is equal to -5. All right, and that is our answer. Okay, this matrix corresponds to a system of linear equations that has exactly one solution. Okay, these are the variable assignments that work. Okay, x has to be -5, y has to be 14, Z has to be -2. Okay, so you can write the answer this way. Okay, you can write it as an ordered triple. Remember, X has to go first, then Y, then Z. Okay, so that's another way you can write the solution. Okay, so we just did this whole problem without using Gauss-Jordan elimination. Okay, it only worked because this was an upper triangular matrix because of all these zeros that were here. Okay, you could have done a similar thing if you had a matrix where the zeros were over here in the top. Okay, but again, if you have something like we've experienced in the past, let me just pull something from a prior example. This was example 4A. Okay, when we wrote down the first matrix, okay, there weren't very many zeros. There was only 1 0. So, you know, translating, well, this matrix came from these equations. The process we just did wouldn't work here. Okay, it only worked in this example because there were so many zeros in the right places in the matrix. Okay, so if you have an upper triangular matrix or if you have a lower triangular matrix, writing out the equations and kind of working backwards would be an alternative to doing Gauss-Jordan elimination. Okay, you could have done Gauss-Jordan elimination on this matrix. Okay, it probably just would have been more tedious and a little bit longer. This is probably an easier method, but the drawback is it only works if it's an upper triangular or a lower triangular matrix. Okay, so again, when you have your test, you'll have a problem, something like this, where, you know, I give you a final matrix or something that's been solved partially, and you have to give me the solution to the corresponding system of equations.